So before I turn to the next topic, which is falling balls, a couple of observations about sort of logistical things. First off, people have asked about WileyPLUS, which is it's this website that has an electronic version of the book with multimedia stuff to it. The figures are videos, many of them, for example. It also has a practice area on asking you questions and leading you back and forth between the questions in the book. That practice area is called Orion, which is an acronym for something that I don't remember. And then there are real homework assignments that are on there. First off, if you're faced with a choice between the WileyPLUS, the WileyPLUS and the binder book, the WileyPLUS and the ebook, I think what you want is just, well, you're fine with just the WileyPLUS. That's the whole shebang. If you want some other version of the book, a paper version or a book I believe that's portable, that doesn't require internet access, then you can get the other options. But the WileyPLUS is enough. And it's got to be the one for this course, which is the most recent edition, 6th edition. Any questions about getting that access to that website? I mean, that is the textbook for this class. Yeah. Would a 5th edition print version be good? The answer is yes. It's pretty close to the 6th edition print version for this semester. I made a fair amount of changes to the 2nd semester material, but the other semester, it's not a 2nd semester, a different semester. Yeah.
In the documents online, we have different sections for this reading.
Yeah.
We read those online and do the corresponding practice. We get that at the end of the
Thanks.
semester.
Yeah. This new version of the website, so it's new to me, it's as new to me as it is to you, has options. I can sort of require various things or assign things. The reading I can assign, but it's not graded. And if it just drives you nuts having me assign it sort of aimed at the day that I plan to start to talk on it, tell me and I can stop doing it. But it was my thought was to assign the reading targeting the day when I'm going to talk about it. The reason for doing that is if the first time you encounter some of these ideas is when I say them, they may be so foreign to you that they'll blow right by you, and you would do better to have seen them at least a little before coming to class. Okay, that's my dream. The dream is to have everybody read all the material before class. In class, we can have a grand discussion about stuff and not even worry about the content. In reality, that never happens. We're all human, and so I will, unless you tell me otherwise, I will keep assigning the readings. They are not graded. If they go past you, don't worry about it. Orion, however, is assigned. Okay? And here now, it's an experiment for me. It's when to make the deadline for that. You do best with Orion when we've worked through the chapter, because it asks about the chapter material. So I have to experiment with it too. It may be possible to do Orion questions just for the sections, and that might be more appropriate. I have to play with this. In any case, I don't mean to penalize you or pinch you for time. Like, we just barely got through the material. You have to do the Orion stuff now, or the deadline arrives. I don't mean to have that happen. So I can change things, I believe, if I've set the deadline too early. The purpose of the Orion stuff is to have you interact with the material, in effect, while there's time to go back and forth. And it's more graded on participation than on accuracy. Like, if you get 60% right, it's 100%. That's perfect, okay? It's meant to be learning experience, not a torture. The homework assignment is actually graded. When you get to the homework assignment, hopefully you know the material well enough that you actually can answer the questions pretty much accurately and be done with it. Yeah?
Sorry, where is the difference in the location on Orion of the homework assignments and then
Yeah, the assignments, I think, are available under assignments. There's a pull-down menu of assignments. The Orion is associated with each section. As you look at the outline of the book, which is one of the other pull-down tabs, you'll see the content, and then you'll also see right next to it a tab for Orion. And I need to play with this too, so I know what I'm doing with it. I would show you, but I don't even know my password. It's down. Never write down your passwords. Yeah. The PowerPoints. That at least I can show you. If you look at the class website, which I'll bring over here. I'm historically an atomic physicist. R.A.B.I. Rabi, Isidore Rabi, was a sort of a famous atomic physicist, and we all can trace our lineage back to him. So this is the website. It's on one of my servers in my office. And two ways to get that schedule. One is this link right here, schedule, click. Alternatively, you can go to the syllabus and get schedule. Either one, you get to the same place. In here, this is a live version of the thing that I gave you at the beginning of the semester. These links, for example, falling balls, if you click on that, it will give you the slides that I'm going to use today. Okay? And after the class is over, I post video. So you can't open this file. I don't want to fix the problem. Modern, well set up computers. There are three possible formats for the video. It's the same video you see on this right-hand screen here. Yeah. The problem sets, yes, thanks. The problem sets are also part of WileyPLUS, and you'll find them under assignments. And I believe I've got 20. There are 20 questions. Yeah. Is there a difference between problem sets and Orion? Yes. Orion is an adaptive learning system. That it watches you getting the questions right or wrong and tries to concentrate in the areas where you're having trouble and send you back to the textbook to try to fix it. It's graded, 60% or more is perfect, okay? The homework assignment is a really graded assignment. It's like taking a mini quiz or something like that. Is there a cap on the number of questions in Orion? I actually don't know. I think I might have set it at 20. Okay. Evidently, there's no cap. Yes, I'll need to investigate that myself to see whether enough is enough. If you got it, you got it. But thanks for asking the questions. So, particularly in this website, since I'm learning it too, I appreciate your help. Other questions? Yeah. Homework is problem sets. So there's Orion and there is problem sets. I mean, I historically call them problem sets because physicists have just done that since Newton was a boy. But homework is another perfectly good term. Yeah. I believe Orion, as I've set it up, covers part one of laws of motion. The first Orion, it's the whole thing. What would be nice for me to go discover as soon as I can is whether you can subdivide it and find just little pieces of it. I think that may be the case if you go into a single section. You can find Orion for just that section. It would make good sense. And it would be more appropriate than waiting till the end. Other questions? I appreciate you asking the questions. I mean, this is the point of actually having a live class is interaction. Otherwise, as a plastic audience, not very useful. Okay. My last thought before going back to the material is my first office hours since the semester started are this afternoon in Alderman Cafe. So I hold my Wednesday morning office hours in my office and my Monday morning office hours over in Alderman Cafe, which is the entrance to the library, the main library. And the purpose is just come and talk about content or other things if you like. I'm happy to talk about anything. If more than one person comes and several of us can talk together, it's actually, You learn a lot from each other and from each other's questions. And so my office hours historically are underutilized. So it's what I do. So come and talk to me. If you've got questions about this stuff or anything, I'm happy to talk to you all. I don't bite. I used to, but I fixed it. No, I'll stop. Okay. So where we left off, my office hours are 3 to 5, just to finish the story. Okay, so where we left off last time was the story of skating. Skating is very much the story of inertia. So skaters spend a lot of time approximately inertial. What's it mean to be inertial? It means moving as inertia had in mind. And to do that, a skater needs to be experiencing no overall force, no net force. If they're experiencing zero net force, they're moving inertially, and they're following Newton's first law of motion, which is to say they move at constant velocity. If they're motionless, they stay that way. If they're moving, they move straight and true, steady pace. Constant velocity. Is that okay with everybody? To leave the inertial mode and to do things like speed up, slow down, or turn, they need to accelerate. And so a skater accelerates, like everything else does, by obtaining a force. Something's got to push on the skater. To speed up, they need to be pushed forward. To be slowed down, they need to be pushed backward. To turn, they need to be pushed to the side. And so the forces cause accelerations. And different skaters accelerate differently according to their mass, which is the measure of their inertia, how much they resist accelerations. And the more massive a skater is, basically the less they accelerate, the less their velocity changes with time as you push on them, assuming you push the same. Questions about those ideas? I'll harangue one last bit about mass. Mass is not the same as weight. I'm about to really dwell on the difference there. Mass has nothing to do with gravity. Weight does. Mass is all about how hard it is to make an object accelerate, to change its velocity. And you can go into deep empty space where there's sort of nothing around, gravity's just irrelevant. And if you go up to two people, the littlest kid in kindergarten and the sumo wrestler, and you try to shake them, and you go to jail for shaking the kid, but so shake the child gently, and they accelerate easily. They accelerate away from you and speed up that way. They accelerate toward you, speed up that way. It's easy to shake something with low mass, like a baseball. I can change its velocity. Oh, right, left, right, left, right. I'm doing lots of acceleration on this. The ball's accelerating. I'm exerting forces back and forth. This is easy. In contrast, the bowling ball now, much harder. And interestingly, you might notice that I'm accelerating a lot myself because, as we'll see, I don't need to put it off forever, but there is one more Newton's law, the third law, which says that if I push on something, it pushes back on me equally hard in the opposite direction. So as I'm shaking this ball and causing it to accelerate one way, the other way, back and forth, it's doing the same thing on me in the opposite direction. And I'm accelerating back and forth. Okay? Any questions? All right. So falling balls. With skating, I didn't specify, didn't name any forces or anything. There are forces around, but we're now going to encounter our first force, and that's the forces due to gravity. So my introductory question, just to get started here, is suppose I throw a ball upward, so I'm going to throw it essentially straight up. It will be into the air because I can't get rid of the air. But after the ball leaves my hand while it is still going upward, so not yet, not yet, not yet. Now, it's heading up, but I'm not touching it. And if we neglect any air effects, is there any force pushing the ball upward? So while it's rising, not at the top, not on the way down, on the way up, is there any force pushing the ball upward? You okay with the question? How many say yes, there's a force pushing upward? How many say no? There's no force pushing upward. Okay, it's probably 3-1 in favor of no. If there's no force pushing the ball upward, why is the ball still going upward then? You tell me. Inertia. That is the right answer. It's going upward not because something's pushing it upward. In fact, something's pushing it downward, gravity. It's going upward because inertia says an object that's left to itself keeps doing what it was doing. Moving upwards, perfectly good. It's got an upward velocity. It wants to keep that upward velocity. It does for a while. It gradually loses that upward velocity because it isn't free of forces. It's experiencing the force due to gravity, a force we call the ball's weight. Okay? So the correct answer to this question is no, there's no upward force on the ball if we neglect air effects. It's moving upward not because something's pushing it upward, but because of inertia, its own tendency to keep doing what it was doing. All right? So, some observations about falling balls. First off, if you drop it from rest, it starts motionless for an instant. The story hasn't started yet because I haven't let go, but right there. It was motionless for the instant I let go, it was motionless. And then it started moving downward, and it was going faster and faster and faster and faster. And you might wonder, well, how do you believe that it's going faster and faster the whole time, or does it just leap to large speed and then go steadily? And you know the answer to this. I won't. Usually I'll have somebody put their hand out here. You don't mind if I drop the ball like this, right, on your hand. But we go up to 10 feet and I drop it, you're kind of more hesitant. You know it goes faster and faster. In your gut, you know that the things coming from great height are scarier. So the longer it has fallen, within the limits, which we can talk about at some point, the faster it is traveling. Okay, what about if you throw it up? And oddly enough, a ball that's thrown up is still a falling ball. So on the way up, it's heading upward for a while, but it's going slower and slower. So it's got a velocity that's upward, but less and less so as time goes on. There is a moment at which it's motionless. It's just a moment of no duration. And then the ball descends from up there as though it were dropped. It's as though someone had it up there and let go. So that's the other possibility with a falling ball. There's straight up. There's just drop from rest. And then the third possibility is if a ball is thrown not straight up, but rather at an angle, travels in an arc. And where did that arc come from? So we'll look at that too. Okay, and these are things that you know intuitively. You know where the ball is going to be if someone throws it at you. You know where to stand to catch it. All this stuff is sort of practically hardwired into your being, but now we'll describe it in terms of physics. So I've got these 6 questions to pursue in order to sort of flesh out the whole story of how a ball falls. So here's the first one. Why does a dropped ball, so you drop it from rest, which is physics jargon probably. Dropping from rest means that it was not moving, and you let go. And that's from rest. Okay, so if I use it so automatically, I have to remember, oh yeah, it's physics jargon. When you do that, it doesn't stay put. If inertia were the whole story, if this ball were free of external forces, and I let go of it from rest, it should stay at rest, right? Object at rest tends to stay at rest. It should just hover there. And it would be really cool if I could do that, if I could switch off gravity. And I can do it in video, and I've done it a couple times. But I'm always careful not to have a flashing sign saying, this isn't real, right? It's a fake. But the fact that it descends tells you it's experiencing a force. It's accelerating downward, faster, faster, faster. That's acceleration, has to be caused by a force. And what is that force? Well, it's the force due to the Earth's gravity on the ball. And the shorthand name for the force due to the Earth's gravity on the ball is the ball's weight. Those are exactly the same idea. Right? So when you talk about your weight, what is your weight? It's the force that the Earth's gravity exerts on you. Forces have directions, and in the case of weights, they are always right toward the center of the Earth. Specifically, it's the Earth's center of gravity, which for our real Earth is pretty much dead center in the middle of the Earth. So the fact that we define downward as the direction things fall, that is aiming right smack dab at the center of the Earth. Of course, it differs for different locations, so someone in China will disagree about the direction of gravity down there, but that's fine. Okay, so weight it's a force, and it's the force due to the Earth's gravity. That distinguishes it from mass. Weight and mass are not the same. Remember, I told you that's coming down the pipe. Mass has nothing to do with gravity. It's how hard it is, in effect, to accelerate something, to shake it, for example. Weight is not mass. It is how hard Earth's gravity is pulling down on something. All right? So, drop ball accelerates because it has a weight, and the weight causes it to accelerate. And that means its velocity changes with time. Any questions? Okay. So question 2 is, how differently do different balls fall? And the answer is not differently. They all fall together. And that might be a surprise to you. So I could use the bowling ball, but we all know what happened when I drop it. Okay? It happens by accident from time to time. Probably will happen this semester. So if I drop all these balls at once, so I've got a baseball, I've got a tennis ball, and I've got a bouncy ball. Ready, get set. They all went down together. I dropped them at the same time, and they all headed down. They went faster and faster and faster, and then they hit the ground, all simultaneously. And that's kind of a strange thing. I guess I could have asked you in advance which one will hit the ground first, and you might have had an opinion different from all of them together. But that's the way it is. They all go together. And why is that? Well, to flesh out that story, I need to start with the observation that all balls have a weight. Gravity pulls down on everything you've ever encountered. It pulls down on these balls, gives them a weight, and the weight of each ball turns out to be proportional to the ball's mass. So what does that mean? It means if you take any ball, pick one at random, okay, baseball. This baseball has a certain weight. I'm not quite sure what it is. It's whatever. Okay, it's got a weight. You know what a baseball feels like, right? And it's got a certain mass. This is a little less familiar to you. You have to shake it or accelerate it and feel its mass. Okay? If you divide one by the other, how hard gravity pulls down on it by how much mass it has, you'll keep getting the same number, the same quantity, 9.8, and it's in units. To finish that story, I have to introduce a metric unit, the metric unit of force. You're used to forces, probably most familiar for the vast majority of you, to forces measured in pounds, and there are other variations, ounces and stuff. But you know what this weighs about 1/3 of a pound. You should know the weight of a baseball. I've looked it up a zillion times. I think it's 5 ounces, so it's about 1/3 of a pound. Okay? But the pound is one of these American oddball units. The metric unit of force is the Newton, for obvious reasons. Sir Isaac, remembering him. How much is a Newton of force? Well, it's about how hard a small apple pushes on your hand when you hold it up. It's about the weight of a small apple, just to give you something to hold on to. So 9.8 newtons per kilogram. A kilogram you're more familiar with. It is the metric unit of mass. So if you take the weight of a ball, measured in newtons, and you divide it by the mass of a ball, measured in kilograms, You keep getting the same value, 9.8 newtons per kilogram. Every kilogram of mass weighs 9.8 newtons. So this this bowling ball, to figure it out, it's about 7 kilograms. So because it's got 7 kilograms of mass, which you do this to figure out, it has 9.8 times 7, which is about 60 some odd newtons of weight. You okay with that idea? This applies to everything. It's actually, people have been looking for a violation of this observation. They've been looking for 1 kilogram of stuff. Pick different stuff. 1 kilogram of water, 1 kilogram of lead, 1 kilogram of gold, 1 kilogram of plastic, 1 kilogram of air. And they've been looking for one that didn't weigh 9.8 newtons. And they're looking to the 23rd digit. They're way out there in the picky details. And no one has ever found a violation of that relationship. And it's kind of, for you all, it might seem like, oh, well, who cares? But for physicists, it's kind of a remarkable thing because kilogram is about mass, how hard things are to accelerate. And newtons in the form of weight are associated with gravity. What do these have to do with each other? Why should mass and gravity stuff have anything to do with each other? They do, and it turns out that observation ultimately led Einstein to figure out what's known as his general theory of relativity. The observation that mass and weight, maybe they're more connected than they appear. And ultimately they are. But that's a story for some other class. Okay, so every kilogram on Earth, here near the surface of the Earth, weighs 9.8 newtons. It's an approximate. It's not an exact figure. And actually, depending on where you are on the surface of the Earth, it varies slightly. If you go into the mountains, it becomes a little weaker. Gravity gets weaker. If you go in deep down, gravity gets a little stronger. It turns out the Earth itself is not perfectly spherical. It's not a ball. Why? Because it's spinning. And the fact that the Earth is spinning once a day, approximately, flings out its midsection. It's actually wider at the equator than it is at the poles. So when you're on the equator, you're a little farther from the center of the Earth in this flung out Earth than you are when you're on the poles, and therefore you weigh a little less. Gravity, you're farther from the center of the Earth, and that weakens gravity a little. It's not zero, it's 0.5%. So you can lose weight by heading from here, heading south. Right? So when you go home for, if you live, okay, the jokes are all obvious. I won't say them. All right. So, question, sort of, this is a mostly, were you paying attention question. A quarter, so a large U.S. coin, so quarters and dimes. There's a lot more metal in a quarter than there is in a dime. And if I drop them, you can imagine what will happen. I'm going to ask you a more specific question here, though. That is, compare the coins' masses and their weights. You okay with the question? The first possible is the quarter has the same mass and the same weight as a dime. How many think so? Okay. B, the quarter has the same mass but more weight than a dime. How about C? Quarter has more mass but the same weight as a dime. And lastly, a quarter has more mass and more weight than a dime. Yay! Okay. Yeah, the quarter has something like 3 times the mass of a dime. And that by itself would mean that, what did I say? Quarter has 3 times the, did I say mass? Forget. It has 3 times the mass of the dime. That by itself makes it harder to accelerate. And if that's the only difference between the two, and I drop them, the quarter would lag behind because it's hard to accelerate. And the dime would hit first. But suppose it was different. Suppose the quarter had more weight than the dime, and that's all the difference. In that case, it's pulled downward harder. If I let go of them, the quarter would go faster, and it would hit first. It would accelerate faster. But that's not the case. The fact is the quarter has about 3 times the mass and 3 times the weight. So when I drop them together at the same moment, they go down together. The fact that the quarter has more weight perfectly compensates for the fact that the quarter has more mass. So it's pulled harder, the quarter's pulled harder, but it resists more, and they cancel each other perfectly, and everybody goes down together. Can you follow that idea? That's why everything falls together. When I was doing I did an online version of this class, which is still available on Coursera, and one of the things I did, I spent a lot of time filming things thrown out of the 3rd floor of this building into the back, the dirt out, the grass out behind that building. So I was throwing everything, including this bowling ball went out there a whole bunch of times and left a wonderful number of dents in there. And I would throw a whole handful of balls out all at once, and they all go together, including the bowling ball. Eventually then, I dropped a camera with the balls. So you do the little GoPro. Down it went with the balls, and everything's falling together. And the cool thing about that is, because the camera was, as opposed to me jumping out the window, right? Would be fun once. But if you with the camera going, what you see with the camera going with the balls is the camera falls, the balls fall, they all fall together. Everything just sort of hovers there in your view. The world is leaping up at you in this camera view, but it's all falling together, and you can experience this. One of these days I'll annihilate myself doing this, but since I'm gonna cheat, right? This is always scary. Okay, as I descend, if I'm more ambitious, I would leap off there and go down. But the balls hover in front of me as I fall, because I'm falling with them. We're all falling together. Try this at the pool on a high dive. Go jump off. Make sure you jump into the water. I'm thinking of the advertisements associated with the Olympics of the guys at a pool crashing on the pool. I don't know. If you saw them, great. If you didn't see them, great. But everything falls together on Earth here. And that's because every kilogram of mass acquires 9.8 newtons of weight. Everything falls together. I've harangued on that a bunch. Hopefully that became clear. Questions about that idea that things fall together? Yeah. Is that when there's no air resistance? Yes. So this is thanks for the question. Because you notice my first introductory question, I said neglecting air effects. I had to do that because air does affect this stuff. For example, sheet of paper. So if I drop the sheet of paper, the claim is everything falls together. I mean, at present, this has a very small mass, but it also has a very small weight, and they perfectly cancel, they perfectly compensate. It's experiencing 9.8 newtons per kilogram, and if I drop these two things together, they'll all fall together. Oops. The problem was air resistance, right? So one of those nuisance effects that I keep trying to sort of get rid of, and here, particularly at the beginning of the semester, I do various tricks to try to make the roles of these nuisance effects, like friction and air resistance, as small as possible. And here I'm not doing it. But if I did get rid of air resistance, that's the next question here. Oops, is it? It's here somewhere. There. There. If I get rid of the air resistance, would the ball and the paper fall at the same rate? Yeah. And how can I do that? Any ideas for how I can get rid of the air resistance? Well, create a vacuum would do it. And that's sort of the classic physics approach. But the simpler approach is to let the sheet of paper follow behind something that gets the air out of the way. This is a phenomenon known as drafting. So if you've ever gone bicycling behind another cyclist or running behind another cyclist, that cyclist basically drags the air with them and leaves an air pocket behind them which offers very little air resistance for someone traveling at the same speed behind them. So I'm going to let the paper draft the book. They're not attached to each other. The book is not pulling the paper down. It's merely getting the air out of the way so the so the paper can fall properly. Down it goes. Okay? So air resistance matters. When the paper is falling badly like this, with terrible air resistance problems, it initially falls, it accelerates downward properly, but it very quickly begins to get this upward breeze blowing on it that begins to apply a second force to it. It's not only experiencing its weight downward, but air resistance upward. And that air resistance force eventually becomes as strong as the paper's weight. When that happens, the paper descends at a constant velocity because it's experiencing no overall force. Its weight is down, the air resistance force is up. You okay with an upward air resistance force for something that's falling down? It's then descending at a velocity that's given a name. It's called terminal velocity. So that you've probably heard the term terminal velocity. This is what it means. It means that something that's falling in the presence of air initially goes faster and faster as required by this whole process of accelerating in response to its weight. But eventually it doesn't keep accelerating. The upward breeze it's experiencing eventually slows its acceleration and gets rid of it altogether eventually. So people experience this process too. You jump out of an airplane and initially you're falling. The airplane's moving, so it's got a little bit more complication to it. But pretty soon you're going faster and faster and faster and faster, and then not so much faster because the breeze up at you is so strong. And people hit terminal velocity of about 100 to 200 miles an hour, depending on how you're oriented. And here now is a case where how many of you have skydived? Okay, so a dozen or so. And you discover that you don't keep going faster and faster. You eventually sort of come down like on an elevator with a tremendous wind up at you, right? Big wind. What do they tell you? I've never done this. I'm not likely to do this. I mean, not without somebody pushing me. Done it. If someone is falling, here's one person going down. Here's you going. Them. They get rid of your air resistance. So these huge, the snowflake patterns people will occasionally create. Jumping team going out of some 747 or something like that. They come down as this huge assembly of people. What makes that so easily hard to do is they have to be very careful about going over each other because they end up going into the air pocket above each person and messing up and hitting each other. You okay with the idea? Okay, so yeah, anyway. Okay, I do want to go backwards here. I want to take a look at that observation that here near the surface of the Earth, every kilogram of mass acquires about 9.8 newtons of weight. Well, there's a name given to that constant, that 9.8 newtons per kilogram. It's given a wacky name. It's called the acceleration due to gravity, which seems like it has what's that doing there? I mean, gravity's involved, and it's maybe acceleration, but where did that come from? Well, here's where it comes from, where that name comes from and why it's appropriate. If you look at Newton's second law, which I introduced last time, the skater's acceleration in response to a force and mitigated by the skater's mass. The acceleration of any object, in this case a ball, is going to be equal to the ratio of two things. The net force on the ball divided by the mass of the ball. This is the resistance to the cause. The effect is acceleration. Well, that's true of going to deep space. That's true of any force you exert on the ball and the ball. But here on Earth, when you let go of a ball and neglecting any effects again to the air, the ball is experiencing only one force. The ball is experiencing only one force, namely its weight. That, incidentally, is the definition, in my view, of a falling ball. A falling ball, or falling anything, is an object that is experiencing only its weight. That's the only force. All right, so if you take the weight of the ball as the force in this Newton's second law of the ball. Well, this ratio of weight of the ball to the mass of the ball, we've seen that before. Each kilogram of mass acquires. That's this thing, this 9.8 newtons per kilogram. So the acceleration of a falling object, in this case a ball, it is that 9.8 newtons per kilogram. The units look weird, though. Acceleration, I haven't done much, talked about this much, but objects' positions are, in the metric system, position is in meters, the distance from a reference point. The velocity is in meters per second. That is, how quickly the position is changing with time. And acceleration is in meters per second, or meters per second squared. That's how fast your system. Yeah. Okay. But we got exactly the same unit as meters per second squared. Why? Because it turns out the Newton is a composite unit. It is secretly, if you open under the hood, what's a Newton? A Newton is the force that causes 1 kilogram of mass to accelerate at 1 meters per second squared of acceleration. So the Newton secretly has pieces inside it. And the pieces inside it, and I'm daunting or anything, when you rip apart the Newton and look at the pieces inside, you end up with 9.8 meters per second squared. The point is, why do this? The point is, two interesting observations, seemingly unrelated, but finally, what I've talked about lies their relationship. That every kilogram of material here near the surface of the Earth weighs 9.8 newtons. And that's one observation. The other observation is that all falling objects, anything that is experiencing only its weight, and therefore is accelerating due to gravity, accelerates downward at 9.8 meters per second squared. These are very, very closely related observations. This neglects air resistance and the slowing effect of air. Is that okay? Well, with that then, let me zip through a couple of other tidbits to this. I keep saying near the surface of the Earth because gravity changes with location. I told you about going to the equator versus going to the poles. But what if you go to the moon? If you go to the moon has a very different gravity. It's got a lot less. With the origin, I don't need to talk about the origin of gravity, but it does have to do with the mass that's exerting the gravitational force. The moon's got much less mass. It's also much smaller in diameter. When all the dust settles, it turns out that the acceleration due to gravity at the surface of the moon is not 9.8 meters per second squared or 9.8 newtons per kilogram. It's just about 1.6. It's about a sixth as strong. So if you were to go to the moon, it would be very easy to set the solar system record for the high jump. Gravity's a lot weaker there. That means when you throw something upward, you throw a basketball upward, instead of slowing to a stop quickly like we're used to, it would slow to a stop 6 times slower, during which time it would go way up higher. You'd easily hit the ceiling of this room with a ball traveling that fast. It would just, gravity isn't pulling back very hard. So during the era of the Apollo missions, for example, one of the astronauts who was a golf fanatic did a little bit of golfing on the moon. Golfing is a complicated story because a golf ball does care about the air, and the air is actually a good thing for golf balls. They fly like an airplane. We'll get there, but that's later in the semester. So air is good, and the moon doesn't have any, so that's bad. So all else being equal, the golf ball would not go as far on the moon as it does on Earth. However, gravity is so weak on the moon that he wasn't taking a full swing because I think the suits were not suitable for that. But the balls were going off, and I guess the little moon people were running around getting the balls miles and miles away. All right, you're going like crazy. All right. A little bit of the story of how a ball falls. And this is a case where watching the new videos as opposed to the old still image figures would be helpful. The ball, once you drop it, that chart on the right is the old version of the story of a ball falling from rest. And its purpose in life, in existence, is to observe a couple things. First off is when you drop a ball, its velocity begins to change because it's accelerating. The acceleration is absolutely constant. I mean, it's for all practical purposes, it's not changing at all. The ball is accelerating downward at the full acceleration of the gravity. That is to say, 9.8 meters per second squared downward. Minus sign is a shorthand for downward in this drawing. So it's a steady downward acceleration, but that does not mean that the ball's velocity is constant. In fact, it means the velocity isn't constant. The ball's velocity starts at 0, and after 1 second, it will have accumulated, by virtue of this downward acceleration, a downward velocity of 9.8 meters per second. And after 2 seconds, it will have accumulated yet another 9.8 meter per second of downward velocity. And after a third second, yet another 9.8 meter per second of downward velocity. So the point is, the ball's velocity keeps increasing with every second of fall. Okay? So the acceleration is constant, but the velocity is not. Faster and faster and faster. And the third piece of this, and I think I'll call it a day at this, is that the ball covers distance, but it covers ever increasing portions of distance as time passes. During the first second, its average speed is rather low because it starts the second motionless, and it finishes the second traveling downward at 9.8 meters per second. That's, on average, about 4.9 meters per second. That's why it travels only 4.9 meters. So the first second, the thing doesn't travel very far. Second, it actually travels 3 times as far. The third second travels 5 times as far. Why does this matter? Other than it goes into one of my favorite questions for exams. That if you watch something fall, during the first half of its fall in time, it travels a very small portion of the distance. So this thing takes not even a full second to fall. But if I divided that falling time in half, I'll have to animate this because it happens too fast. But if you go to the halfway point in time, the ball is not at the halfway point in distance. It's only at a quarter of the way point. That first half in time, it doesn't go very far because it's going so slowly. It's the second half that it makes all the progress. So, where is that useful? Other than answering questions, I have to think about it. But watch things fall. Okay, so next time I'll finish talking about falling, a few more details, and then we'll move on to ramps.